All right, welcome back Science 30s to our next lesson in chapter 6. This is 6.2, and today we're going to look at the universal wave equation. In the last video, we talked about a whole bunch of different types of waves. We talked about mechanical waves, electromagnetic waves, transverse and longitudinal waves. And we tried to animate it using this diagram of what's supposed to represent a string and the particles of the string moving along in a line. And we talked about if you shake one end, the disturbance is going to get passed through the string. How we're going to start looking at the wave properties of velocity, wavelength, and frequency is by showing how you can make different shaped waves by shaking a string in different ways. So we're going to start with just shaking it at kind of a medium pace here, where you lift that side up, bring it down, and the wave pulse gets transferred in this direction. Okay, if we go at that rate of lifting that side and bringing it back down, we get a wave that kind of looks like this, or it's part of a wave. It's just the top part, which is sometimes called a pulse, but it's about that big. Hopefully you can see that that was about the curve that we were getting coming in this direction. But now what we're going to change is if we go quicker on that side, imagine someone was holding that particle and went up and down faster, that would make the wave look more like this. So at that end, it's going up and down faster, and it created a wave, or in this case, a wave pulse, that was closer together. This is a shorter wavelength. The length of the wave is shorter because we went up and down faster. If we went up and down slower, this one's going to be going really slow. It shows if I went really long, it's going to make a really long wavelength. Okay? So the faster or the more frequent we move that end of the string, the shorter the wavelength, and the less frequent, the more slowly we move it, the longer wavelength. That one would look kind of like this. Okay, now looking at velocity, if we shook the same string in all those different ways, whether it's slow or fast, the wave should move through the string at the same velocity. So if we have the same medium that the wave is going through, we should have the same velocity. So I'm just going to show some waves moving across in this direction now. The shorter wavelength at the top, medium, and then the longer wave at the bottom, and they're all going to be moving the same rate across the screen. So even though they're longer or shorter, as long as it's the same medium, they should all move at the same velocity. And so now we've mentioned three properties of the wave: the wavelength, the velocity that it moves at, and the frequency. I talked about it, the frequency of that the hand was moved or that the wave was generated. But now we're going to look at that frequency kind of as the rate that peaks are going to be hitting this side of the screen. So I've highlighted the peaks on each one of those waves, and think of frequency as how frequently a peak gets to this side of the screen. And hopefully we'll see that the shorter wavelengths with the peaks closer together has more frequently peaks hitting this side of the screen, and then it's going to be less frequent in the middle and the least frequent at the bottom. So let's take a look at that. Hopefully we can see on the top, the frequency of seeing peaks get to the edge of the screen is highest at the top and lowest at the bottom. So this relationship right here, that as I decrease the wavelength, I increase the frequency, is one of the biggest relationships to take away from the universal wave equation. We haven't actually looked at it yet, so let's look at the universal wave equation. Its formula is V is equal to lambda F. Lambda is a bit of a new symbol for us to see in this course. Lambda means wavelength. It kind of looks like a weird shaped N or kind of like an H, and it stands for wavelength. F being frequency and V being velocity. So velocity is going to be in meters per second, wavelength is going to be in meters, and frequency is kind of being in per second or cycles per second, which is also called hertz. And just to emphasize that relationship again, the velocity, as long as it's the same medium, is going to stay the same. So as long as we're shaking through the same spring, water's moving through the same water, light's moving through the same medium, whether that's air, water, or a prism, as long as it's traveling through the same thing, the velocity is going to stay the same. So then if we increase the wavelength, make it a longer wave, we are going to decrease the frequency, and vice versa. If we make the wavelength shorter, the frequency would then be higher. So to keep velocity the same, if one of these goes up, the other one must go down. That's an important relationship to know. Another relationship that isn't asked about as often, but is another important one to know, is what happens if we do change the velocity, we go into a different medium. And the idea is that if we increase the velocity, this is going to cause an increase in the wavelength. The frequency is not going to change. So if we change the velocity, the wavelength has to change as well. It's going to change the same way the velocity does. So if velocity goes up, wavelength's up. If velocity is down, wavelength's down. But the frequency has to remain the same even when you're changing mediums. So now let's look at doing some calculations with this. And because this chapter is focused on EMR, we're going to look at some calculations of electromagnetic radiation and the universal wave equation. So we're going to assume that the light's going to be traveling in air or a vacuum where it goes at the speed of 3.0 times 10 to the 8 meters per second. Let's just pause there for a moment. 3.0 times 10 to the 8 meters per second. That means it goes 3.0 times 10 to the 8 meters every single second. That is crazy, crazy fast. It's the fastest that anything we know of can go. It's 300,000 kilometers every second. We almost can't put that speed into perspective because we go nowhere near this speed. I mean, imagine if we had a map of going across Canada, and that's approximately 5,500 kilometers. How long it would take us to go across Canada would be a long time. How long does it take light to go across Canada? About 0.018 seconds. It's a very, very, very fast speed. And this number is given to you on the data sheet. It's not too hard to find and use in equations, but we should just appreciate for how incredibly fast this stuff is moving. Now let's look at when we keep that the same, because the speed of light is going to be the same for all EMR. They all go at the speed of light. And again, we're assuming in a vacuum where it's going the 3.0 times 10 to the 8. Let's look at some frequencies and wavelengths. So a reminder about their kind of relationship to each other. From the last lesson, we saw that low energy light has a long wavelength. And now from today's relationship, we know that it has a long wavelength. It's going to have a low frequency. So that would be something like this. I put it with red because red is the longer wavelength of visible light that we can see. And if it has high energy, that means it's going to be a shorter wavelength. And from our relationship today, know that is going to be a higher frequency. And I can put that in blue, showing a shorter wavelength, higher frequency here. Again, showing it in blue because blue is a shorter wavelength of visible light. So let's do a couple calculating examples. This one says red light has a wavelength of 700 nanometers. What is its frequency? So we'll throw up the universal wave equation of V is equal to wavelength times frequency. And we're trying to rearrange for frequency. So all I have to do is take the wavelength and put it on the other side. So V divided by our wavelength. We'll throw in our numbers. 3.0 times 10 to the 8 meters per second for V. 700 nanometers, so 700 times 10 to the negative 9 meters for our wavelength. And we get a value of 4.3 times 10 to the 14. So not too difficult of equation, just with 3 variables, not too hard to rearrange and move around. Let's take a look at another one. This one says a radio signal is broadcast at 91.7 megahertz. What is the wavelength of this radio wave? Okay, so this one we're just looking for the wavelength. We start with the same equation, V is equal to lambda F. Again, for all EMR, we're going to have the speed being 3.0 times 10 to the 8, as long as it's in air or a vacuum. So we throw that in there and divide by our frequency. Solve for the wavelength. Let's put our numbers in there. And I get a final answer of 3.3 meters. So that's actually pretty long, especially compared to the last question where we're dealing with nanometers, and it just shows the scale and the variety of different types of EMR. So hopefully that has helped you to understand what the universal wave equation says in terms of its relationship between velocity, wavelength, and frequency, and shown you how to do some calculations. That's all we have for this video. Thank you so much for watching, and I'll see you in the next one.